So, well, we see here that you learn about work and energy, right? And we define what is work, what is energy. Okay, so energy is the ability to do work, right? You can see my screen, yes?
Yes, sir.
Okay, so energy is the
Yes.
ability to do work, yeah? So when you have an energy, when force is applied, when you have a force is applied, there is an energy transfer. Because there is an energy transfer,
Work.
there is work. Okay. So we also says that work and energy are not independent. We are saying that work and energy is related. They are related somehow. Okay. And we also know that if you apply a force to this block, right, and this block will move a certain distance, or let's call it displacement or distance. Okay. Therefore, work is simply equal to what?
Force times distance.
Yes, force times the distance. Okay. And we did some examples about work, yeah. And we did derive the formula for kinetic energy, right? So work is also equal to kinetic energy, which is equal to 1/2 mv squared, right? So kinetic energy is what? What is kinetic energy? Energy that causes the object to have motion, right? And an energy that causes an object to have motion is what you call a
Kinetic energy.
kinetic energy. So the formal definition of kinetic energy is energy due to motion or work needed to accelerate an object at rest to its current velocity. Kinetic energy ni definição ni maka work energy due to motion or ni definição ni fala kata kinetic energy is work that is needed to accelerate an object at rest to its current velocity. Katak work ida nebe o precisa ato iha, ato halo, ato acelera objeto ida ba ninyo velocidade ida nebe presente ne. Basta? Now, we also learn about potential energy, right? You learn about what is potential energy. Potential energy ne mana ba? Lo sala imi aprende con potential energy is mass times gravity times the age. And you also learn about the law of conservation of energy. So, mi aprende law of conservation of energy diyan sa energy cannot be created nor destroyed, but it can only be transferred from one form to another. That's what the law of conservation of energy is. Okay, and we did some examples, and I asked you to do homework number 3. I hope everybody submitted already. Betul tama na to?
Same.
All right. So that is so today we are going to learn about force, a work done by gravitational force. Yeah. Maybe o ini te kuliah kono ba work done by gravitational force. Okay, so work done by gravitational force. Okay, so for example, ano yan? So work done by gravitational force. Ne tetong karik diyan sa ne work ina nebe accomplish nebe usa ato halo ato precisa benene ato halo work ini te precisa sa ina. Work is what? The definition of work is what?
Um,
What is energy? Definition of energy is
energy.
ability to do work, right? Maybe at halo work ito thank you energia. Lost to?
Yes, sir.
Agora, ato ida
Enjoy
energia
mahirap.
bahiro apply força ida ba? Niya se causa e energia to. Nebe agora força nebe o apply in this case nebe ito narang gravitational force. Okay, nebe imagine niya sa ne ida ne ita ni imini niya ground. This is your let's suppose this is your ground. Yeah. This is the ground. Right? And then you have a box of object, say this size, and obviously this object has a mass. Those are now, panghira o aplica força ida ba if when you apply a certain force to this object, when you apply a certain force to this object, oops, sorry. Pahira ita aplica força ida ba objeto ida ne, what happens to this object? What happened to this mass? It will
It it will
it will
move.
move up somewhere in this distance, right? But it will not stay there. Let's get it. So let's just write it as a let's just write it as a like this as a instead of writing it as an actual box. Let's just write it as a all right. So it will go up, right? And that is the height of that, right? So let's say so this let's call this the height of this. Let's get it. Now
Yes,
what
sir.
happened after it reaches this point? What happened?
It falls down.
Yeah, it falls back down, right? So, but
Mm.
we can also calculate the work for this. Let's call this work by force, yeah? So you're applying a force, right? You're applying a force. So the work that is done by this, so the work that you done by applying a force is what? How do you calculate that? It's just simply the force multiplied
Uh,
by
mm,
by this
by the
displacement or the
yeah,
distance or the displacement, yeah? Now, what is the force here? Force sa saída makihane. Force yan ene saída mahatene.
the box.
Yeah, the force, but there is another force that happening here. When you apply a force upward, there is also another force. You call that a Newton's third law of motion. Newton's third law of motion is diyan saída. When you apply a force, Newton's third law diyan saída. For every action, there is an equal and opposite
Direction.
reaction.
Right.
For every action, there is an equal and opposite reaction. So when you apply an action of force going there, you also have an opposite direction. Force, the normal force, right? Or the weight. So we call this, so this is the weight, or just simply the mass times the gravity of that. Terus guys, ito ini comprende ito?
Yes, sir.
Okay, so therefore, ito niya force, the summation of force upward or downward, vertical is just simply, so F is just simply equal to the mass. Then force is just simply equal to the mass times the gravity. Maybe ita taufali henekadik, ita niya work done by the applied force is simply the mass multiplied by the gravity multiplied by the displacement. Or displacement in this case is what? Ito niya displacement yan masayda. It's just simply the height. Let's get all right.
Yes, sir.
So and at that point, on your box na nene, oing na nebe niya tote na ba, niya muno filafali? Negala, niya sate ba na ba, niya muno filafali mayo na? Agora, bahira niya muno filafali mayo ne, apakah o apply tam force rumah ba kalaya na? Ha? Bahira niya tote alete niya muno filafali mayo. Do you apply an external force? No, yes, but
No.
the external force is what? The force of? The force of? Gravity. Nebe, the work done. Nekan ya muno filafali mayo nekan? nia forsa ne be applicable objeto mun fina fale mana ma forsa ida det forsa molnaran molnaran
Gravity.
gravitational
Force
gravitational force, yeah. Okay, so let's call this the work done by the gravitational force. It's equal to the force of gravity multiplied by the displacement. Ito niya, force of gravity niya, Saira. That is just simply the mass times gravity. The displacement mo, Sanesa, is just simply the h. Yeah, force of gravity is just mgh. Sanesa mo, Saira. So, I know, this is not a very complicated concept, but uh, it's a pretty simple concept. But let's do some example, all right? All right, so let's suppose we have this. Okay. All right, so a ball of mass m equals to 0.5 kilogram is dropped from a height of 10 meter above the ground. Assuming no air resistance, okay? Okay, por exemplo, yan ito niya bola naman eh. Let's suppose this is your ball. This is your ground. Okay, so this is the ground. Nidiyan as a name. A ball of mass, so let's call this a ball, this big ball over here. Bola ito niya masa hira? 0.5 kilogram.
5 kilograms.
Okay, drop from about the height of 10 meter.
10 meter.
Okay, so suppose this is your scenario. Assuming there is no air resistance, we want to calculate the speed of the ball just before it hits the ground and the work done by the gravity. How do you calculate the speed? Remember, yeah, ita ita kuliah ko na ba? Ano yeah? Oh, how I look at this, I don't even about conservation of energy, but anyway. So, baseado the law of conservation of energy, ni diyan sa law of conservation of energy, ni diyan sa law of conservation of energy. Ni diyan katak. The initial potential energy na be initial. Yeah, let's call it potential energy 1 plus kinetic energy 1 niya thinking hanesa mo sa potential energy ke 2 plus kinetic energy 2. That's what it simply means. Okay, nebe ya momento neka por ejemplo ini o ni 5 maka. Let's posisi na ita baru dihang initial ini. Let's call this is an initial position. And this is the final position. Okay? Now, ito niya, potential energy, ito niya kinetic energy, initial niya kalaya.
None.
None, right? Because it's not moving. The mass is not moving. Yan na ba niya, may tilo sa na ba? Berarti ito niya kinetic energy na pertama na sana. Zero.
Zero.
You don't have it. But you do have the potential energy, lo salen? On the potential energy ba masa ida ne masa ida? On the masa multiplica ba a gravidade, multiplica ba a canebe ihane. Lo salen? Agora, equal to, agora potential energy ia be position finale ia kale. Potential energy ia position finale ia kale. Bahira bola ne ni husi lete na ba? Ni mai monu te fare to ia krai kene. Ni potential energy se ia kale.
Yes. Layam.
Layihona. Tama sa naman layihona tamba. Ninya agane layete na ninya height ne layete na lo sala. Deve potential
Yes.
energy ne massa times gravidade times the height. Berarti tine potential energy da ne mo so layihona. Maybe itine kinetic energy ne iya hela sebelum it hits the ground. Kinetic energy kinetic ne saya mass H inisial ya, H1 ya. Itu nih formula kinetic energy ini saya 1/2 mass times
Times
the final
Times
velocity square.
velocity.
Yeah, this velocity square. But in this case, this is velocity number 2. Yeah. Let's call this. Yeah. Let's do initial. Initial. Let's call this number 2 is final instead. Never lali kal confusion with that. Okay. So mv final square. Ok, agora mi atendo na sana berarti ini formula mgh equals to 1/2 mvf square lo salah. Então massa ida ne massa cancela out tia. Ita karak bukan ne maka velocity berarti 2gh is equal to vf square. So ita ne vf is simply equal to square root of 2 times g times h. Lo salah? Ah, hansana sana ona berarti ita ne ita ni niya be. Tahu? Tatene katak itane gravidade ne is just simply 9.8 meters per second square. Itane h ne saida. H ne saida?
H is 10 meters.
Yes, 10 meter. Okay, so that will be meter square per second square. So that's the answer of what? What is this answer?
For final velocity.
Yeah, 2 times 9 square root of 2 times 9.8 times 10. That will be 14. Yeah. So we will get 14 meters per second. So this is your velocity. Okay. Now, any question? So is that it? But the question is, we want to find two things. Assuming we will calculate the speed of the ball just before it hits the end, the work done by gravity. Itamos atene kata karak buka mo the work done by gravity. The work done by gravity na masayda. The work done by gravity is just the work
Mhm.
the work done by gravity is just simply the change in potential energy, which is just
Energy.
simply yeah, it's just negative change in potential energy. That's what it simply means, which is just equal to in initial potential energy initial minus potential energy final, right? But you know that potential energy final is 0. So potential energy initial is just simply mg and hi. So it's simply mass times the gravity times, so the mass is what? What's our mass? It's 0.5 kilograms. Gravity is 9.81. The height is also 10. So the work by gravity is simply 49. What's the unit for work? What is the unit for work? Joule.
Joules. Yeah.
Okay. All right. But this work is also the same thing as this work is also equals to the change in kinetic equals to the change in kinetic energy. okay, where you have delta kinetic energy, just simply the final kinetic energy minus the initial kinetic energy. So the initial kinetic energy is 0, right? So it will just be 1/2 mvf squared, which you have 1/2 mass times 0.5 times the velocity. You know velocity to be 14 squared. So it will just be the same answer, 49 joules as well. Okay. So that will just be kinetic energy, so delta Ka. So in all the kinetic energy, this is why conservation of energy applies, right? Okay. Any other questions?
None, teacher.
Okay. Let's do a couple more examples. All right. What about this one? Okay. All right. It says here that a block of mass equal to 2 kilograms, it slides down a frictionless incline of height 5 meters and a length of 10 meters starting from rest. Calculate the work done by gravity and the block speed at the bottom of the incline. Okay, maybe need to understand that. So suppose you have an incline like this, yeah? Suppose this is your incline. Okay, and suppose this is your ground. This is your ground. Okay, this is your ground. A block of mass m, let's call this block of mass m. Okay, let's call this block of mass m like this. Okay. Right, so let's just rotate it a little bit. Okay, suppose this block of mass m. And this block has a mass of, let's say, 2 kilograms. Okay. Now it slides down of the height of this is, let's suppose the height of this is, let's say, the height of this is 5 meter. And the distance over here is 10 meter. Okay. ¿Comprenden el problema, to? A block of mass
Yes.
m, 2 kilograms, slides down, assuming this sliding is frictionless, yeah? This is no friction. This is a frictionless. Frictionless slide. This is we assume that. A block of mass, 2 kilograms, slides down a frictionless incline of height of 5 meters and a length of 10 meters. Starting from rest. Starting kata hanene. Starting niya rest. Dia para hela. Dia labokan ya. From rest. Kata niya para. Starting from rest. Calculate the work done by gravity and the block's speed at the bottom of the incline. Okay, how would one calculate that? Well, you can use the conservation of energy, right? So later on, at the final position, this is your initial position, and your final position, the box will be here, right? Will stop over here. Last time? Make sense?
No.
Yes, true.
Okay, so your initial position, so using the concept of conservation of energy, Conservation of energy ni din sila. The potential energy initial plus the kinetic energy initial should be equal to potential energy final and then plus kinetic energy final. Okay, so now that you have this, now what is zero in this assumption? Assumption si rin ini, hindi mo zero. Potential energy initial ka, kinetic energy initial ka, potential energy final ka, kinetic energy final. Ito na mo zero, zero.
Potential energy initial and kinetic energy initial.
What? Repeat, please.
Potential energy initial and kinetic energy initial are both zero.
No, not really. Why you make this conclusion? Explain.
Because it since it's going to the lower side, that means the initial energy doesn't, that means you don't have an initial energy velocity for it, so
Yeah, that's correct. Yeah, initial kinetic energy is zero. That's correct. But why does initial potential energy also zero?
um
No, it's not zero. Okay, it
oh,
has a potential energy.
oh,
Okay, what else is zero? Saitama zero. Ademia, Saitama zero. Ademia, what else is zero?
Is near H.
No, itania iniziale, potential energy initiale, yeah, ma potential energy finale.
Or kinema.
Potential energy final is also zero. Tamba niya total ni harai dan ini nini aga layat tenan ni aga zero tenan ni. Wala na may tini potential energy ni zero. Okay, comprende na to?
Iya, comprende.
Okay, ito oy calcula tena, ito ni bita tena tena katak. Ito ni VF equals to square root of 2G and H. Yani oy ita calcula tena to, ito derive tena. Okay? Ito buka sera. Ito the work done by gravity speed at the bottom. Maybe ini speed ni simply 2 times 9.81 times the height of what? Yung height niya sara? 5 meter.
5 meter.
VF is simply equal to 9.9 meters per second. Okay, unsahon niya be the work done by gravity. The work done by gravity naman si tena work done by gravity is just simply negative of delta potential energy, which is just simply mg and IH in so. So which is just simply equal to 2 times 9.8 times 5 is equal to, which is just equal to 98 joule. Okay? And that is work done by potential energy, work done by spring to change the kinetic energy. Okay? Any questions? Preguntas?
none, teacher.
Okay, let's do one more example over here. Okay, what about this one? Okay, it simply says a crate of mass 10 kilograms is lifted vertically upward by a crane at a constant speed of 2 meters per second over a height of sabi natin crane. Crane natin ito. Pabayin be biasa ema be hit sa amin. This is the crane, yeah. This is what you mean by crane. Okay, so very good. So okay, so this is the crane. Crane naman yeah. So just imagine this is a crane. It lifts up. Até na ito side ng crane ni. Kasi a construção sila ba may hit sa sun side.
Yes, teacher.
So just imagine this is a crane that has it lifts up mass of an object. The initial mass in, let's say this is the initial ground. Let's suppose you have a crate of mass. Let's say a crate of mass 10. Okay, so this thing has a mass of 10 kilograms. Okay, it lifts it up vertically upward at a constant speed, yeah. It lifts it at a constant speed. Lift up na constant. Usi initial position ba nene at a constant speed like this. Okay. So just imagine this crane over here. Let's just delete this. Let's just do a crane. Imagine that any hits high, lift up, yeah. So go over from here. This is the ground, and then let's lift up to that. Ni velocidade da neve ni go ne. It's what 2 meters per second over the height of 3 meters.
That's
Okay. Now, we want to calculate the work done by gravity and the change in kinetic energy. We want to calculate the work done by gravity and the change in kinetic energy. Which how many tathal na? Huh? Okay. Nebe ita tene katak. Since the crane is moves at constant velocity, yeah? Constant speed. Okay. Since the crane moves at constant speed, the net force is what? Pahirap buat ida maka-move at constant velocity, berarti ini akselerasyon na sa You move up sa nena, it's a constant velocity, constant velocity. Então, akselerasyon na sa is 0.
0.
So, since akselerasyon 0, então niya força be se akselerasyon maka 0 if acceleration is 0 since velocity is constant. Ito na força na sa net force na sa Imagine força na niya formula sa
Or force times distance.
No, force. What's the formula for
force?
force?
massa times
Aceleração.
Massa times acceleration.
acceleration.
Maybe yan ita niya acceleration sa 0.
Zero.
Therefore, ita niya net force is also
0.
Zero.
Logical line? Yes. The net force is equals to 0. Nebe itania be crane ganin itania crane niya forces nene crane ida be yanene niya forza nene balance by let's suppose niya balance tiya ba iha let's maybe put this maybe put this any heat to itani niya be but naman ida naman heat but ne jadi crane niya force ne the force of the crane is balance the gravitational force nebe aplicable ne kalau bahira o heat sa ne força gravidade emos do tung mai lo sala antam força nebe crane ide ne aplica ba massa ide ne ni hanesa mos ho força gravidade nebe aplica mais sekarang maka ite ne crane ne mala força berarti força gravidade sei tebe monutrit mai lo sala ite la heat sasane la moving at a constant velocity of 2 meters per second. All right? Comprende, Tony? Non è problema.
Yes, teacher.
Comprende?
Yes,
Okay. Então, ita bele buka ita niya gravity. The work done by gravity is simply what? It's just simply yeah, it's just mass times the height.
Gravity.
And you
Yes.
know mass to be 10 kilograms, the gravity to be 9.81 meters per second square. The height is to be 3 meters.
Meters.
So therefore, you have
Negative 94.
no, but this has to be a negative because it's pointing downward. Yeah, I forgot the negative over here. Okay, so you have negative 294
2000 joule.
joule. Okay. Maybe estamos a tener que the work done by the work done by gravity. Nemane, itamos bele usa potential energy. Itamos bele usa the work done by gravity is also equals to the negative change of potential energy, which is just equal to potential energy initial minus the potential energy final. Okay. All right, but you know that potential energy initial is just 0. That's why you have negative 10 times 9.8 times 3. That's why negative 294 joules. The same thing. So sound one and isn't it? 294 joule. Okay, so since the speed is constant, the initial and final kinetic energies are equal. Mas galay? Tambah ito niya be speed ni constant berarti initial kinetic energy initial nene hanya so kinetic energy na be final. Tama sa sinabi ni speed ni constant because since speed is constant, initial kinetic energy is equal to the final kinetic energy, which is just simply equals to 1/2 mass times v squared. 1/2 times the mass is 10 kilograms. The velocity is 2 meters per second square. So, the kinetic energy is simply equal to 20 joule.
3 joules.
Okay, so this is your answer. And this is your answer. All right, so delta Ka is delta Ka with Ke, which is delta kinetic energy final minus kinetic energy initial is what? Is equal to 0. Tama siya naroon hanesan din. The change in kinetic energy is 0 because the velocity is constant. Okay? Comprende? Preguntas?
None, teacher.
All right. Right, so that is work done by gravitational force. Agora itaba fali. Bolunaran. Work done by spring force. Okay, that will be now. We are going to talk about work done by a spring force. Okay. All right. What exactly is a spring?
It's a piece of metal that what was it? Allows something to jump upwards.
Yeah, this is a spring. Yeah. So imagine, imi sa imi niya ready na to. Imi have a Borracha biasa have lapiseran na laran ni basic ka buar ni laran ni panhare to. Panhare kala. O
Then,
pera o da rumah bebe sir imi semi huma ali bebe ya karek biasa be. Tara yu uma leten be ta doko bebe tun sai ne. Ate ne to?
boy.
Ya boy ne ya base ne me ta larang spring ne. Okay, that's what you call spring. So then imagine you attach block it and imagine you have this block over here. You're attaching this block to it. Nebe, ita tahu posisi asalnya ini ita tahu dia posisi zero ya. Let's suppose this is a zero position. Tambah linear dan ita tahu zero position or initial position, or we call it equilibrium position. Later we call it equilibrium potential. Name. Nebe, ya posisi ini agora da rauk ne. Ita niya força ne zero. Ita sedang apply força ida ba. Ita niya x ga distancia demo still zero. It's still not moving yet. Okay. Nebe, yeah, spring force. And in spring force, nene, spring force of the spring, force never applica who see the spring over here. This is the spring. Okay. Ida nene, ita the force is equal to K, negative of K times X. Okay, remember this formula. This is K multiplied by X. Ida nene mabolo Hooke's law. Okay? Scientista nara Hooke's naman. So K ne makaitan niya spring constant. Spring constant. Ne katak se banhira, por exemplo, imitau besi rua, por exemplo, imitau besi kaya besi oi los kala, i stainless steel, iha iron los kala. Nebe spring constant ne specific baka di material sa ida ita uja nesa spring ya. Okay? This measures stiffness, measures spring stiffness, yeah. Stiffness na yan, nasa por exemplo, imidara tali, imidala, se ema na irua makadara tali ho dada besi, por exemplo, ema ida ya sorine kartali, ida tanya sorine kartali, senar dada malu, los galay, ne tali se kotu, los to? Los galay.
Yes, true.
May be maka senara karfal besi, ida karfal sorine kartali, besi ne se la kotu tamba, besi niya K ne spring constant ne makahli fali taabe. Tali the venenine spring constant. So never spring constant is material specific to a different material. So K is material specific. Okay. At katak materia ide ninya iha spring constant iha. Okay. And the unit for K the K nini unit ne maka iha Newton per meter. Ya, ne unidad de K ne mane. Okay. The unit for K is in Newton per meter. Okay. So that's what we mean by spring force. Ne mane. All right. So let's do a different scenario. Okay. Let's do I want to do this scenario. All right, so this one is the scenario that I was talking about. Okay. Then imihari look at like. For example, imihari linha ida venene, linha ida nene, nema equilibrium ya. Por exemplo, iha clara nema imini equilibrium nema ne. Nekat ida sida kalu batida ba. Nema imini linha nema imini initial position. This is your initial position, okay? Initial position. Hare to?
Yes,
Mihare
teacher.
okay, this is your initial position. If when on your x kata bahira or dada sai or dada to on initial kan ihare halete na bane or dada lo segala on initial ne or dada ida block ida ne initialmente hene ne dada sai te fala bana ba. Ne artinya ba lima karo. Berarti if x is positive, so when x is positive is positive. Ito it halsa na the spring is stretch. Comprende sa stretching gale. Kata or
Yes,
dada.
teacher.
You stretch. Therefore, the force is negative. Remember, ito force na sa force is equal to negative k and x. Sa karik maka ito ni x na positive, berarti o multiplika ba kaya na niya sa resulta iha negative value. Nasalah? So therefore, your F force of the spring is negative. Okay, when x is at 0, when x is at 0, or we call it at the equilibrium position. Spring is at the equilibrium position. At equilibrium. Katanya ni avokana. Ne makita nene. So this one is this one. This one is this one. F is what? F is 0. Yeah. Tambah x is 0, therefore F is 0. Maybe when x is negative, spring is compressed. Kata hanihan, dulu tama balarang. Okay, therefore F is positive. Comprende to?
Yes, teacher.
Understand, yeah? Any questions? Sa perguntas rumah kono ba name?
None.
All right, so you have an initial position and which is this one. When you compress, compress kata o dumeti hamutuk o dumeti ang suhasan niya o husik de repente sa dama kontese. Otomatis buat na sa halay bakbabakman sa neto. That's correct. So push
Yes.
it will just moving back and forth like this. All right. Maybe ito niya. So Hooke's law. Yeah, Hooke's law ni madiyasan this is let's call this Hooke's law. So Hooke's law says that Hooke's law is saying that the force exerted is always the force exerted by a spring is always directed opposite to the displacement of the equilibrium. So the F is called spring force. F is called spring force. Or restoring force, sorry. If block is released, if block is released, it will oscillate back and forth between negative x and positive x. Naman sa mga hadihan eh. Sa karik maka, if you release this will moving back and forth, those to that, or may farane, ni baba bamayad ta sa nelos tara. You just go back and forth like this. That's what the Hooke's law means. Right? All right. And then okay, so for example, if this is the case, then what is our x and what is our so what is that? So that will be, so in this case, okay, maybe for example, to initial position equilibrium na mahane. This is our equilibrium. Ito the initial position. This is the equilibrium position. Ay hira odada tiya may hene, odada tiya may kotok inenable stretching ka compressing. X positive ka negative.
X is positive.
X is positive. Therefore, the force has to be negative. So the distance debe odada nebe kuburo narang on displacement. Yeah, this is what you call your displacement. Yeah, the distance debe o odada nebe kuburo narang ita ni imini displacement ne. Okay. Maybe ita ni forza is just simply the force of that is just simply the force of that spring is just simply the force of the x is just simply negative k times the x distance na ita ihani. So it's simply like that. So long as you know that already. Okay. Now hanesa mo so karik se karik ita iya fali sito sango ida hanesa na eh. Ita ne compression lo salay. This is your equilibrium. Okay, so this is your equilibrium. Maybe push the mass na ba showing na ba? Okay, since you push this mass, and then your x is the distance from initial equilibrium to this position over here. That's what your displacement is. In a formula, it's the same formula, yeah? Pregunta so far? Any questions so far?
None, teacher.
So the work done by spring force is this. So work done by spring force is this. Dinya assumption naman eh. The assumptions naman eh. Okay. Spring is massless. Ita asumi kata spring ni niya massa laya ya. Spring is massless, which just simply means the mass of the spring is very, very small, that it's negligible. Much more than the block, that it becomes negligible. That's what the assumptions are made. Yeah. So the ideal spring obeys the Hooke's law exactly. Okay. See, constant between the block and the floor is contact between the block and the floor is frictionless. This is what we are assuming. Block is particle-like. Okay? All right. ¿Hay preguntas, Ruma, so far?
No, teacher.
All right. Nebe, por exemplo, nessa, né? So, ito na calculação, itahala ko ka nessa, né? Let's say calculation. Suppose ida ne makaita niya be. Naman ya. Imagine ida makita ne. Ida fali maida ne lo salay. Nebe, salah satu sudah na duan, eh. Bahira imi. Iha scenario ne mas sana san los gala niya force ne baba ba mai de niya work of the spring. Bahira odada tida ne. Odada tida ne, odada ida be ne, odada ida ne, initial position odada tema ne, o husi ko ne lima sa ma acontece. What happened when you remove the hand? Okay, let me just show you let's see if we can find spring force animation, yeah. And Hooke's law. Okay, here it is. Okay, can you see my screen?
Yeah, teacher.
What do you see?
Nice. I see the video.
Video, teacher.
Okay. All right.
As simple harmonic, examine the motion of an
Okay, so
Or
just
mass.
imagine this, okay?
If we pull this block so as to expand the spring, and then we release the block, it
Maybe pull initially
will
ne.
have a particular mass. If we pull this block so as to expand the spring, and then we release the block,
Agora me pull, depois me husi what
it will
happened.
vibrate back and forth
Yeah.
between more compressed and less compressed states. If we assume that the surface of motion is completely frictionless, then the elastic potential energy reaches a maximum when the spring is most or least compressed and the block is changing direction, while kinetic energy is at a maximum when the block is right in the middle and moving the fastest. If we were to graph the position of the block against time, it would display sinusoidal behavior, just like a trigonometric sine function, where the block continues to occupy the same positions over a particular period of time, which is why we call this periodic motion. X equals 0 at the equilibrium position of the block, where it sat before we pulled it, and assuming 0 friction, the block will oscillate between positive x and negative x indefinitely. In reality, frictional forces will dampen the spring's activity, and it will eventually come to a stop. But for many systems, an ideal mass spring system will be a decent approximation for a real one. Of course, every spring is different. Some are loose, like a slinky, and some are stiff, like the spring that launches a pinball into play. This factor is represented by the spring constant K, which will be unique to a particular spring. The force that a spring can exert is equal to negative K times the displacement of the object it acts upon, and this relationship is called Hooke's law. The negative sign indicates that the force of the spring is always opposite the direction of the movement of the object. When the object compresses the spring, it will push out, and when the object stretches the spring, it will pull in. In both cases, the spring is attempting to move the object back to its equilibrium position, which is why the force applied by the spring can be called a restoring force. The units on a spring constant will be newtons per meter, so that when you multiply by some distance x, you get the force that must be applied to compress that spring that far. Let's also note that the elastic potential energy of a spring will be equal to 1/2 kx squared, where k is the spring constant and x is the distance it is stretched or compressed. If at equilibrium, the distance is 0, so it has 0 elastic potential energy, and the maximum elastic potential energy will occur at the maximum distance from this point on either side of the oscillation. This expression looks similar to the expression for kinetic energy, which is convenient since the two will interchange as the mass oscillates. A pendulum also displays periodic motion since it swings back and forth between the same two positions. Although this involves gravitational potential energy rather than elastic potential energy, and we will look at this behavior next. Let's check comprehension.
Okay, so that's it. That's the potential energy stuff. All right, so all right, so that's it. That was the so if I were to calculate the force, okay, so if we were to say the work of the potential energy, so the work of the spring is just simply equal to the summation of the forces, the force multiplied by the delta x, yeah, the change of x, because the delta x is always like moving back and forth, so that will be the summation of this. Okay, so the summation of the force times the delta x. Okay, but we also saying that delta x approaches 0. So basically what we are saying here is that, so imagine if you have if you were to plot between, say between your force in y axis and then your x in the f axis, so the plot will look like somewhere like this, yeah. So it's somehow like this, something like this. Okay, so at the initial x, that's a less, so it's about force. So at initial x, let's say at this point is your initial x. Okay, let's call this xi, initial xi, and then let's call this f of xi, right? And then so that will be f of xi is here. And then you have x final over here. Let's call this f x of f, right? The final f. Let's call this f of j. Let's call this f of, yeah. All right. So ita hakarak atu buka ini kan we minimize the difference. Yeah, this is the delta x. Yeah, this is the delta x. If you remember your calculus, you're trying to minimize the differences in that. So that's why. So at every time the spring is moving, delta x is it's very, very small, right? So technically speaking, if we can convert this into a derivative expression, so this one just becomes the integral of the x initial to x final of the force times the derivative of x. That's how you convert this into that. Okay, you can just convert this into this, which is simply doing, if you take this, the integral of f of x, and you know that the f is just equal to negative k of x times dx, right? So, but k is a constant, so you just take out. So all you left with is x of dx. So x dx is just simply x squared over 2, right? So that will just simply be 1/2 of k times x squared over 2 of x initial times x final. So that will just give me negative 1/2 times the k times the x of final square minus x of initial square. So this is your W of S. Okay, so this is your spring constant with between final and initial. But we can also or we can just simply write the work spring constant as just simply negative, or just write 1/2 of k xi squared minus 1/2 kxf squared. That's also or. You can also just simply write negative 1/2 kx f squared if your x initial is 0. If only sekali itong x initial them as 0, then you just use this formula over here. Okay, you can do this to this to this. Okay, so these are the formula that we are going to be using. So basically what we are saying here is that when Ws, the work of the spring is approaches 0, okay, when the work of the spring is approaches 0, what we means here that the block ends up closer to the relaxed position or equilibrium position, ends up closer to the relaxed position. Or equilibrium, yeah. When your Ws, then it was initially. Now, when your work spring constant is less than 0, that simply means that the blocks end further away from x equals to 0. Okay, and then if your work spring constant is greater than 0, oh, sorry, yeah. So this one was greater, yeah. If this is equals to 0, blocks end up at x equals to 0. Tapi hanya sa way mi hare ni spring da ohin mi be niya. Baku main ni ni at some point ni niya sa stop wala sa makin tempo ba sa makin niya stop onam. Nabe bahira maka niya halo atividade ne maka niya mono liu te fale ni original katak o niya bene, for example, sakali blocks are further away from x equals to 0, that's the work is less than 0. Okay, so this is what it means. All right, questions?
None, teacher.
All right, we'll do example next meeting.